In the previous video, I introduced you to the continuity equation, or at least to the version of the continuity equation which is given in introductory textbooks. Here's the idea. Let's say that we have a fluid flowing through a pipe, and somehow the pipe gets wider or narrower. If we assume that the flow is steady and incompressible, then there is a simple relation we can make between the flow speeds in the two segments of the pipe. Basically, what the continuity equation says is that as we go through the flow, the product of the cross-sectional area and the flow speed is a constant. So in this figure, we have on the wide side, cross-sectional area A1 and flow speed V1, and on the narrow side, cross-sectional area A2 and flow speed V2. The continuity equation then gives us A1 V1 equals A2 V2. In this video, we're going to do a short example problem using the continuity equation. Let's say, for example, that we have here a hose of some kind, and we have attached a nozzle onto the hose. Let's say that in the main part of the hose, the diameter is D1, but then the diameter of the nozzle over here is D2. According to the continuity equation, we would expect then that the flow speed as the fluid comes out of the nozzle would be greater than the flow speed in the main part of the pipe. Let's say then that we are given the diameter D1 in the main part of the hose, the diameter D2 of the nozzle, the flow speed V1 through the main part of the hose. So those values are D1, 2 centimeters, D2, 0.4 centimeters, V1, 5 centimeters per second. We want to find then V2, which is the flow speed as the fluid exits the nozzle. Let's start by just writing down the continuity equation. A1 V1 equals A2 V2. I showed you in a previous video how we can relate the area to the diameter rather than to the radius as we are more accustomed. So I'll quickly show how we do that here. So you're familiar with the equation, area equals pi r squared. So to relate the area to the diameter, I just replace radius with diameter over 2. So when I square diameter over 2, I get area equals pi diameter squared over 4. Anyways, coming to the continuity equation here, area 1 would be equal to pi over 4 times diameter 1 squared. Then we multiply by flow speed. Area 2 would be equal to pi over 4 diameter 2 squared times flow speed. So solving for V2 now, we can cancel pi over 4s between the two sides of the equation. Then isolating V2, we have V2 equals V1 times diameter 1 squared over diameter 2 squared. And we are already almost done. We just have to make substitutions. So flow speed 1, 5 centimeters per second. Let me write this next factor as diameter 1 over diameter 2, whole thing squared. So diameter 1 was 2 centimeters. Diameter 2 was 0.4 centimeters. As far as the unit checking, just notice that centimeters cancels centimeters. So we can see that the unit of this whole thing is centimeters per second. Here, maybe even try to do this without your calculator. Notice that this thing in the parentheses is 2 over 0.4. So ask yourself, what is 2 over 0.4? Square that in your head, then multiply by 5 and see if you can get the right answer. Maybe pause the video, see if you can do this in your head. And doing that in your head or on your calculator, you'll get 125. So the speed of the fluid as it exits the nozzle is 125 centimeters per second. And now we have done our first problem using the continuity equation.